Hey Bio30s, it's Manchak here with your very first lesson for our final unit in our course for Biology 30. We are getting started with Unit D, which is Population and Community Dynamics. And so what I'm going to do today is we're going to run you through the first two concepts, D1 and D2, and then we're going to, you'll have the opportunity to practice and do all the stuff that you usually get to do. Just a comment about today. I am going to try something a little bit different. And I'm going to ask for your feedback on this when you guys get a chance. Instead of me recording a couple of relatively long videos of me just talking over my notes, I'm going to try something a little bit different today. And that thing that I'm going to try is I am going to just give you the highlights of what I think is important, and then I'm going to direct you to a playlist of some relatively short YouTube videos I've put together that will allow you to get the information I think you need to get from what's going on here. So I'm going to explain some of the changes that I'm going to implement, and there's one more that I'm curious to see how it goes, and we'll work from there. So we'll play around with that in a second here. So let me explain to you how things are going to work, because I sort of alluded to that. I am going to be giving you guys this quick video introduction to the unit as well as to concepts D1 and D2, and then I'm going to invite you guys to go to in the Google Classroom where you found this video. There's a playlist that I'll ask you guys to go through that will have you looking at I think it's three different videos to cover these first two concepts. The videos are, you can see over here, a little over 9 minutes long, a little over 4 minutes long, and just over 11 minutes long. And they're going to run you through the stuff that you guys need to know for this concept and do a really good job at it. So instead of me reinventing the wheel and doing my own thing when somebody has done it as good or better than what I've done it with, I'm going to try that and see how that works for you guys. So what I'm also going to try is after I've introduced you to the things that I think are key or important to know for this concept, I'm also going to encourage you guys, when you do your practice quiz and when you do your summative quiz, I am going to make them, you ready for it? Open book. So I'm going to make them open book for you, meaning that you are welcome to have your notes in front of you, or you're welcome to have your textbook open, whatever it is, so long as the information you put down is your information alone, and not something that you've copied off the internet, because that is plagiarism. So that is what I'm going to do, which is a little bit different. And we're going to see how it works, okay? I want to see how this goes. If everybody, seems to do just fine with it and we're okay with it, then we're going to go with that. But I will seek your feedback on this later on. Okay, so that's where I'm at. I'm trying something new. I don't know if it's going to work, but I feel like looking at the views on my videos that I put up on YouTube, where I'm only getting 1, maybe 2 views on this, and there are several of you in the class, that tells me you're not using that resource. So maybe I'm just going to supply you with other resources plus my notes and a bit of explanation, and we'll see how it goes from there. Let me know. Send me some feedback on this when you guys do this, and we'll see. But I think I'm probably going to do the remainder of this unit using this format, just so you know. All right, so let's introduce Unit D. So Unit D is our very last unit. It's called Population and Community Dynamics. There are 3 major outcomes that you guys are going to be covering over the course of the unit, and I will cover them in the notes as I always do. The first one is going to be that you're going to describe a community as a composite of populations in which individuals contribute to a gene pool that can change over time. So we're going to bring in some of the stuff we talked about in Unit C into Unit D and talk about it a little bit, but we're getting bigger now. We're talking not about what's going on in an individual cell or an individual organism. Now we're getting into some big stuff. You're going to be able to explain the interaction of individuals in a population with one another and members of other populations. So now we're starting to really get into studying populations and communities and ecosystems, which is what I love doing. And then lastly, you're going to explain in quantitative terms the changes in populations over time. So what's going to happen during the course of this concept is you guys are actually going to be working your way through some things quantitatively as well, which means you're going to need a calculator. So make sure you've got one handy as you move through this. Today we're covering D1 and D2. So D1 is basically the Hardy-Weinberg concept, or principle, which explains how a population should remain, its gene pool should remain stable over time, and how we can quantify that and come up with calculations and those kinds of things. So we're actually going to be using a couple of formulas in this concept, and I'll explain to you how we're going to use them as we move forward. And then D2 is going to be looking at, okay, well, if things aren't being met according to Hardy-Weinberg, then what can lead to the change in the diversity in a gene pool, or the stability of a gene pool? So we're going to look at what could cause a gene pool to change. And that's basically what D2 is. And we're going to be looking at these things called natural selection, genetic drift, gene flow, non-random mating, all of that kind of stuff. That is going to transition us into the remainder of the concepts, and there are only 6 concepts in this unit. So I'm going to take 3 weeks to cover this unit with you guys. So we'll do D1 and D2, then D3 and D4, then D5 and D6, and we will be done. Okay, so what I'm going to do now is just switch this over, and I'm going to run you through the important parts of the notes. So you should have grabbed the notes. If you haven't already, go onto the Google Classroom. Under Resources, Notes, and Worksheets, you'll find these notes here, and print them off or have them handy so that you can highlight and underline as necessary. What I want you to do, and I'm going to switch to this for just a second, is if you want to at this point, you could hit pause on this and go ahead and watch these 3 videos. If that works for you. I've actually put them in a YouTube playlist so that you could just watch them back to back to back if you'd like. It'll be about in the neighborhood of, let's say, about 30 minutes, no more than about 25, 26 minutes of videos to watch. And it's not me, and they're animated and all the other kind of stuff. So if you want to do that, hit pause now. Or if you wanted to continue on, you can continue on, and I'm going to just highlight the important concepts that I want you guys to get from this particular set of concepts. Okay, so I'm going to run through this really quickly and highlight a few things that I would like you guys to know as we move forward. So I'm just going to open up my tools and get my comment thing open for you here along the side, and I want to just make sure I'm going to move my video that I've got my tools ready. Okay, so my highlight tool is right here. Okay, good. So what I want you guys to be able to get from this, the first thing is we're really getting into talking about gene pools and populations, and how our understanding of what Mendelian genetics taught us, so segregation and dominance and all of that kind of stuff, how that jives with what Darwin talks about, which is natural selection and those kinds of things. And so this first concept is really going to talk about genomes, and gene pools. So really take the time to understand that what a genome is, and that is the entire genetic makeup of a particular species, and then really understand that genetic diversity is being influenced by 3 things in particular: possessing a large number of genes. And this is diversity, focusing on that word diversity. More alleles for each gene equates for more diversity, and sexual reproduction leads to more diversity as well, which we've talked about along the way from time to time. Understand what a gene pool is, okay? And then understand what I mean by gene frequency, okay? A change, and this bit at the bottom here that I've italicized, a change in gene frequency results in a change in the genetic diversity of a population, okay? So either a positive or a negative change. So if you've got one gene that's more frequent than another, or one allele that's more frequent than another, then that's going to change our genetic diversity. Hardy-Weinberg is the big thing for concept D1, and understanding what the Hardy-Weinberg principle is. Basically, the Hardy-Weinberg principle says that the original population or proportions of genotypes in a population remain constant from generation to generation, so long as certain conditions don't change. So if you have certain conditions being met, and we'll discuss what those are in a second, I'll highlight them for you, then a population is going to remain the same in perpetuity. As long as if those conditions change at all, then a population is going to change. That's what the Hardy-Weinberg principle says. Make sure you understand what we mean by allele frequency, and I think the videos do an excellent job of explaining that. And maybe have a quick definition of what fixed frequency is as well. The 5 conditions, which the videos did highlight, the 5 conditions that must be met for Hardy-Weinberg principle to be valid are population is large, random mating, no mutation, no gene input, other words, immigration and emigration, and no natural selection occurring. Okay, and I think that you guys should see from the videos, if you haven't watched them already, it should be obvious in the videos that these 5 conditions are really difficult to meet. In fact, they're almost impossible. But what it does is gives us an ideal situation to work our way through with these. Just like in physics, we often deal with ideal situations, like we remove friction because it makes things too complicated. This allows us to communicate what an ideal population might look like if these 5 factors aren't affecting the population. The videos did an excellent job, I think, of relating these 3 formulas to you and how they work. Particularly the formulas I want you guys to use are this one at the top here and this one at the bottom, and you'll use them both. And all 3 of the videos have gone through the explanation of how to actually work with these formulas. Okay, so you should be able to do that. I'm going to record a quick example for you so you can hear it from me too, just so that you guys are ready for that. Okay, this is just describing actually what the Amoeba Sisters video covers very well, working your way through given a certain population of individuals, what's going on. So this is D1, and so what I'm going to do is I'm going to very briefly here hit pause, and I'm going to get set up to record and show you guys this and how it works. So it'll kind of flash away for a second, and then we'll jump into D2 after that. Okay, so I've got this example here that's in your notes. Whoops. And we're going to have a look at how to solve this using Hardy-Weinberg. And so we're gonna play around with this. I'm gonna tell you that there are a couple of worksheets that I would really like you guys to work on as well for this. Do one of the Hardy-Weinberg worksheets at least to make sure you understand the math behind this and how all of this works. It is not complicated math. If you could do a square root or you can square something, then you guys are golden, and there's nothing that you really need to worry about. Okay, so we're assuming that all 5 conditions, of Hardy-Weinberg are being met. Okay, so a population has only 2 alleles, a big R and a little r for a particular gene, and we know the frequency of big R is 20%. Okay, so what that means is if big R frequency is 20%, that's the same as 0.2. Okay, and what we're being asked in the question is what are the allele or the genotype frequencies for the population. Okay, so this is an allele frequency, right? This is our allele, right? What is our genotype frequency going to be, basically, is what the question is asking. So what is the possibility of this genotype, and that genotype? Okay, looks like my video lagged for a second there, so hopefully it didn't mess anything up for you. So we're going to start over here, and we're going to play with this allele frequency. And remember the formula P plus Q equals 1. The P and the Q, remember P is the dominant allele. Okay, Q is the recessive allele, the frequency of those alleles. Okay, so this is dealing with allele frequency. Okay, that's what we're dealing with there. So if we already know that R is equal to this, that means that we have P, because P is the dominant allele and R is obviously dominant because it's capital. So then we can figure out what Q is going to be by simply rearranging this and solving for Q. So Q is equal to 1 minus P. 1 minus 0.2 gives us 0.8. So our frequency of Q then is 0.8. So if our allele frequency for Q is 0.8, our allele frequency for P is 0.2, we could figure out the genotype frequencies for the rest of these. And it should be relatively simple to do that. Remember, we go to the formula P squared plus 2PQ plus Q squared equals 1. Okay? Remember, please, that P squared is the same as big R, okay? That 2PQ represents heterozygous, and Q squared represents homozygous recessive, okay? So if you remember those, that makes this really easy. And all we have to do now to figure this out is just substitute numbers in. So to figure out what big R is, that is the same as P squared. So that is going to be 0.2 squared. And that gives us 0.04 for our frequency. Okay. 2PQ, remember, that's big R, little r. So we're just going to substitute numbers in for that. So it'll be 2 times 0.2 times 0.8. And that's going to give us 0.32 for our frequency of the heterozygous genotype. And then lastly, little r is the same as Q squared. Q, we figured out over here, is 0.8. So it'll be 0.8 squared, which is 0.64. Okay? If we went and we added up all of these, right, 0.64 plus 0.32 is 0.96 plus another 0.04, that gives us a total of 1.0. So we've done our work correctly. That's really how we work with this. You're usually going to use both formulas, okay? Sometimes you might be given the allele frequency, which we were given here for our allele frequency. Sometimes you might be given a genotype frequency. Remember, if it says that 32% of the population are homozygous recessive, or 32% are affected by this recessive allele, then you automatically know Q squared. If you know Q squared, you can get Q, right? Because you can take the square root of Q, right? So if we're given, 32% are little r, let's say, then we know that this is Q squared. So what is Q then? Q is equal to the square root of Q squared. That's just doing simple math. So this is the square root of 0.32. Okay. Once you get this value, you can get P. Once you have P, you can get Q or P squared or 2PQ from that. So it's just doing a little bit of simple math as you work your way through this. So I hope that that's not too challenging for you. So I am going to make this disappear and just pause for a sec. All right, so that in essence is Hardy-Weinberg for you guys and how you work your way through it. Like I said, please make sure you guys actually spend the time to do some of the worksheets, okay? And do a little bit of practice and do one. If you're going to do anything, do one worksheet and then check your answers using the key in the Google Classroom. That was a lot of ums in that sentence there. I apologize for that. So the next thing that we're going to do is let's move on to concept D2, and I'll just quickly highlight the important points that I want you to know. So in D1, we said that Hardy-Weinberg principle explains the allele frequencies and allows us to calculate the allele frequencies in a population that is basically stable and has no things acting on it. It's got a large population. There is no immigration or emigration. There's no mutation. There's no natural selection, and there is random mating. Okay, that does not describe a real population. And I hope you guys understand that that doesn't describe a real population. That's not how the world works, okay? The videos did an excellent job also of explaining, particularly the crash course one, explaining these pieces here. So in real life, IRL, as the kids like to say these days, what happens if we have a small population? What happens if there is migration? What happens if there are mutations? What happens if there's natural selection? What happens if mating is non-random? And let me explain that one quickly. Non-random mating means we actually select mates. And you know what? Nature does that a lot. I mean, look at a bird is not a bright yellow color because it wants to blend in with a green forest. No, it's a bright yellow color because it shows that it is healthy, and that the more brightly yellow or the more brightly colored it is, the more that organism shows its health. That means it's going to be selected for because of that. Okay, so it will breed. So what I want you guys to understand is that this section is all about, okay, what could lead to a gene pool change? And so there are 5 things that we're going to talk about that lead to a gene pool change. One of them is something called genetic drift. Okay, and I want you guys to understand genetic drift. These diagrams, by the way, I'll explain these because I think they're very important, and I pulled these off of a website that is really, really excellent for this stuff. What these diagrams are showing is different populations. There's a population of 20, there's a population of 200, there's a population of 2,000. Okay, notice how genetic drift has its most impact on very small populations and minimal impact on large populations. Okay, and this is just explaining to you what happens if something completely uncontrolled or completely by chance affects a population. So it's a result of chance. That's what genetic drift is. Okay, and genetic drift can include two kinds of genetic drift, right? There's something called founder effect, and understand what that means, and bottleneck effect, and understand what that means. And that's what these diagrams here are trying to illustrate, is founder effect and bottleneck effect. Okay, the next kind of thing that can happen is gene flow, and this is the movement of alleles from one population to another, what we call migration. Okay, that can change the gene pool of a population. Okay, and this diagram is illustrating what would happen if we had bluebirds and redbirds, that they were isolated by a mountain. Well, what if a bluebird went over, and what if a redbird came over? And redbirds are all homozygous recessive. Bluebirds can be either homozygous dominant or heterozygous. And if they go over to the other side, then we end up with changing of the gene pool, because now we've introduced new alleles into that population, which changes the gene pool. The next thing that can change a gene pool are mutations, which we know to be randomly occurring, giving rise to genetic diversity. That can result in a new allele being produced or something along those lines. That one should be relatively self-explanatory. Natural selection we talked about in Bio 20. This is how nature promotes things that are beneficial. The key word here is beneficial to the population. Okay, so it's how nature promotes something that is good that is happening in the population. So beneficial mutations. If it creates a mutation that is making an individual better able to survive, then we're going to see more of that gene or that allele in the population over time. Have a quick look at heterozygote advantage. It pops up from time to time, and it's good to understand. And the example that I give you here has to do with sickle cell anemia. So have a look at that, please. And then the last one is non-random mating, and I mentioned this one previous to you. Non-random mating is called sexual selection. So we're selecting an individual based on what that individual looks like or how they behave, rather than just bumping into somebody randomly. The way I like to look at it is sexual selection is you go out and you choose the person that you mate with, whereas non-random or random mating is you close your eyes, you open a textbook, you put your finger on a name, or sorry, phone book, pardon me, you put your finger on the name in the phone book, and that's the person you mate with, as long as they are of the opposite sex, those kinds of things. So or they're compatible to mate with for you. That's what we're talking about with non-random mating. So those 5 things: non-random mating, natural selection, mutations, gene flow, and genetic drift, when they are present, and one or all of them, then a population's gene pool will change over time. How much it changes depends a lot on the population and other factors that really are a little bit beyond what this course is going to go through. So that's my general rundown of concepts D1 and D2. What we'll move on to next week is D3, where we describe a little bit more about how populations are, the characteristics of them, and then maybe some calculations associated with that. And then we look looking into measuring how populations change as time goes by and actually putting some quantitative values to that. So that's it for this week. If you guys have any questions, as always, please track me down on the Google Classroom, or on the Google Classroom, I like to call it that, or via an email, and we can arrange for a Google Meet, something along those lines. Please make sure you watch the playlist if you haven't watched it already. Again, it's up to you. You can do it before or after. I really don't care. Make sure you have a look at and do at least one of these 2 worksheets for D1. Please have a look at the questions on D2 in the textbook. And then when you're ready, do your D1-D2 practice quiz. You can have your book open, your notes out for that if you'd like to. And then once you've done that and received feedback from me, then you guys can move on to the summative quiz, which is also open book. And I will trust that you guys are not, searching for answers on the internet, anything along those lines. So that is it for this week. Please leave me some feedback after you've got through this at the end of the week, and let me know if this is something that works for you or not. Watch those videos. Find more if you need to. If you find a great one that really worked well for you, maybe share it with me. And other than that, hey, let me know how you're doing from time to time. That is all I have to say for now. We will stay safe, and we will talk soon when we get to concepts D3 and D4.